Hello? Hello? Okay. While we're setting up the panel, how we run this, I just give a quick introduction. So really excited to invite like different companies, and then they are running the OEM supporting us, and then so we're gonna have like a couple minutes for them to make an introduction about the product, and then how they engage with OCP and OAI, and then we're gonna run the panel. I prepared some hard question for them, and then I also wanna all our audience to ask hard question. This is a good opportunity to collaborate, and then hopefully we have a great discussion. Okay.
Before we start the panel, though, I wanted to thank the system vendors who have provided the solutions for the 3 reference designs. May I just ask you guys to just come here and join us? Come on, come on. We have a couple of minutes. Come, take a picture. Come on, guys. All this, we have 3 wonderful reference designs. Come on. There's been tireless amount of work gone into designing these systems. Whitney, do you agree?
Of course, yes.
We've had many weeks of work, late nights, early mornings, gone through a number of reviews, creating slides, creating schematics, reviewing the layouts, and mechanical, thermal, all kinds of aspects. It's been a tremendous amount of work, and just wanted to personally thank you guys.
Thank you.
Thank you. Thank you.
Or do you want us to stall while you get set up?
Well, since we're waiting, do you have any comments?
No, I'm good.
You good?
Sure. Yeah, no, just to echo what Siamak said, there were a lot of late nights, and the cool thing is, I mean, we're all different companies, but just coming together, someone has a good idea, and it sort of builds, and people are contributing, so it's a really cool thing to see, and this OEM is definitely something that is gained a lot of momentum, I think, with the early announcements earlier this year, and then coming into full swing at this regional summit. You can see the crowds just around the OAI experience booth there. It's amazing. So I'm just glad to be a part of it. So.
Thank you. Appreciate it.
Now I'm going to invite AK from Intel. AK, you have 3 minutes.
Good afternoon, guys. I'm AK Roy. I'm a strategy and planning manager in the AI products group at Intel Corporation. And glad to be talking to you guys about our new deep learning processor called Neural Network Processor 1000. Go on to the next one. Okay, so to start off the introduction of the processor, and I have it in my hand, feel free to come over afterwards and have a look. So we are very glad to partner with the OCP OAI work group and come up with this module that is OAM spec compliant, and because of that, we've been able to leverage all your expertise and your experience in the industry over the last generations. And the processor, because of our partnership with OCP OAM, is going to enable us, our customers, and the market to innovate faster, go on to solving the bigger problems in a better way. So let's take one step back and look at what does the market and the customers need. As you can see that over the last few years, the model sizes of our AI training models have grown exponentially. We are already about 1 billion parameters in our natural language processing models, and if you see where the market needs to go, where the big problems need to go to solve, with better accuracy, with more business impact, you can see that the number of parameters in our models are going to just explode. And if you just extrapolate to getting to artificial general intelligence, people say that you need somewhere in the 500 trillion parameter type models to get to that. And so because of that, for sure, what we need, what the customers need, what the market needs is large scale training systems. And that's what this processor has been built to deliver, a large scale AI training system to train these large models. So there are three different architectural issues of enabling large scale training systems. The first is the compute itself. So you got to have a high performing AI compute processor. The second is the communication. Because large scale training models, you cannot fit into one single processor. You have to have hundreds, maybe thousands of processors working together. And so you need that AI processor-to-processor communication. And the third thing is the memory pipeline. So the bigger, the faster memory pipeline you have, the faster will be your time to train. And so you need to have all three aspects balanced and high performing. And that's what this processor aims to deliver. So let me talk 1 minute on our interchip link fabric. So as I was saying, for large-scale training use cases, you need to be able to connect hundreds, maybe thousands of processors in a high-performance, low-latency manner. And our built-in interchip link fabric, glueless fabric, is built for that and allows you to do that. Right now, in this generation of processor, we have the ability to have a fabric at 448 gigabytes per second. And so you can actually connect 1,000 of these guys at that speed. And so that will allow you to train very large scale models in best-in-class time to train performance. Finishing up with software, so the hardware itself is not sufficient to deliver, the time to train performance at real applications. You need also software, and this processor has a fully developed software stack, starting with our compiler stack that allows you to actually compile and optimize at ops and micro-ops level through our Argon ngraph and Argon compiler, and then the last part is the orchestration. So if you have hundreds and thousands of these processes connected together, you have to be able to orchestrate your large-scale training model properly. And so you need a sophisticated orchestration software capability, and that's what we have here too. Going back up to what we call pod-scale training, right? For these large-scale AI training use cases with, let's say, 10 billion parameters, how do you actually orchestrate and run it so that you get the performance and you get the performance at a tractable amount of TCO. So you need to have a pod scale training system design that allows you to do that. And it starts with, again, the AI compute, then it goes on to the communication between the processors, and then on to being able to scale out both the AI compute, AI communication, and power cooling, and then reliability and orchestration. So I'll finish with that, and then call to action is, again, as I was saying, we've had a fantastic journey with you guys over the last couple of years, getting to this point, and would like to continue this journey on to the next generation types of problems. And want to invite you guys to partner with us to deliver the performance that we need to deliver to us, to our customers and the market. Thank you.
Thank you again. So now I'm going to have Rob from Nvidia talk about,
Awesome.
yes.
So much to say, so little time.
Okay, when I get all the bio from our panelists, it's very long, so I'm going to just let themselves to introduce themselves. Yeah.
Sure. So Rob Ober, Chief Platform Architect at Nvidia. I deal with a lot of people here all the time. Super quick. Okay. Nvidia joined OCP about, I guess it was about 2016. We were in the middle of working with two very nice companies, Facebook and Microsoft, on designs based on, which became Big Basin and HGX1, both are contributions in OCP now. These are in production in multiple data centers, and they're both based, the topology, a lot of the core technology are things that were developed by Nvidia and worked on with our partners. The interesting point I'm gonna point out right now is that the topology, the interconnect topology, and the configuration of these systems is fairly similar to what we're looking at in UBB. So there's a lot of similarity in how they operate and how they will perform. These two systems use NVIDIA Volta V100, so keep that in mind. I wanted to say, contrary to popular opinion, NVIDIA is actually a really big proponent of open source, and especially open source software. We are a huge contributor, and we also benefit greatly from open source. We work on an entire ecosystem stack, and here we are. I wanted to specifically point out a few things. One is that we work on all of the frameworks. So all of the frameworks are optimized and tailored to our GPUs. And we're the #2 contributor to TensorFlow, next to Google, who is the developer and owner. We're the #2 contributor on PyTorch with Facebook, who is the owner and coordinator. We're the #2 contributor to MXNet, which is Amazon's framework, and also the #2 contributor to Paddle, which is Baidu's framework. Also wanted to point out that we have open source containers that we deploy. They're freely available. You can rip them apart. You can use whatever you want. They're fully optimized stacks that can be that reflect our record, our benchmark setting performance. Also want to, we open source a bunch of compilers and libraries. Some are closed source. They're more like a HAL layer. We also have communication libraries open, Nickel, MPI, those are contributions. We also have things like libfabrics that we've contributed. And we're actually contributing new types of neural networks that are openly available. Those things are, several of them are actually in production in very large data centers today, and I would assume that most of you people probably use them every day. We have extensions to Docker and Kubernetes that we use extensively in a new superpod architectures. These things are 1,000 GPU clusters. We built these to build our ML perf systems, and we share those entire platforms, the hardware architecture, the physical architecture, the interconnect loom, the bill of materials. We also share the entire software stack, so the management, the telemetry, the load balancing. These things are based on Slurm and Kubernetes. Those things are freely available. And we've open sourced TensorRT, which is our inference compiler and deployment tool, as well as TensorRT server, which is a load balancing Kubernetes-based deployment model to get efficient use of GPUs and the highest throughput of your inference. So leveraging that entire software ecosystem is really important to us, and it helps everybody. And I want to point out that with the launch of different GPUs, these are we have pretty consistently doubled the performance every year. So the same hardware, same framework, same network, same training data. It's about 2x year on year. So we're able to do that because of the open software ecosystem that we're really leveraging. One of the cautionary tales here is the warning that if you build a hardware system, you can assume that the pressure on the CPU, the I/O, the network, the storage is going to double about every year. So you need to plan ahead. You need to over-provision at the time you land hardware because it will get consumed. And part of the result of all that is the ability to have predictable performance that is constantly advancing. So, for example, this is the ML perf results from just a little while ago. You can see most of the entries, the non-NVIDIA entries are grayed out here. Most of the entries are from NVIDIA. They're in everywhere, configurations from single GPU up to 1,000 GPU cluster. And many of these are record-setting benchmarks. Now, if I go back to, say, DGX-1V, the topology, the configuration is very similar to UBB. What you end up is getting a very predictable, advanced view of what the performance of UBB should be. And all of that is a very long way to get around to saying, I guess, I don't know if you saw this in sitting out earlier, but I brought a V100 proof of concept to the conference here. It's fully functional, at least it was when I took it out of the lab. When it gets back, it may not be. It'll run up to 350 watts. You can predict its ML performance because it's going to be very, very similar to what you saw in that other chart. And the whole thing runs on standard AI software. It's all the standard frameworks, the standard infrastructure. And it really is truly based on an open source hardware spec and open source software. So it's really exciting. It's a big event, and thanks.
Thank you, Rob. While I'm setting up, I may ask Frank from AMD, introduce yourself.
Hi, I'm Frank Helms from AMD. I'm a server GPU system architect, and I'm here to talk a little bit about our OAM and OAI aspirations and goals. So I think the first thing that I wanted to say was, I don't know if this is working or not. Is it? I guess it is. Okay. The first thing I wanted to say was basically thanks to Facebook, Whitney, Microsoft, Intel, and others. If you asked me 18 months ago, I would say, hey, there's no way there's going to be an interoperable module between AMD and Intel and Nvidia and others. Now basically the OAM spec exists, and industries in progress on open infrastructure that can take the superset, if you will. The OAM spec is the superset of what's needed for multiple companies' accelerators. And so it's possible with that superset to build universal baseboards that actually are able to support many companies' different OAM. So thanks so much for that. That's a pretty amazing feat. And I guess I already said this, but I do appreciate the work that's been going on since then on the infrastructure that we've heard about earlier today with the OAI and the UBBs in particular, and the systems wrapped around those. And I think this is all just reiteration of what's been said before, but interoperability is really one of the key points. And then, of course, the connectivity and the ability to support different power levels and different interconnect topologies. AMD specific goals around OAM and OAI had to do with being able to support, the connectivity needed for high performance computing and for machine learning, and in particular, I'll say the industry standard complement of 8 accelerators and 8 accelerators with connectivity for communication. So in particular for us, one of the goals is modules with 8x16 links, and in particular, one of the topologies that we plan to support we call chordal ring, which is also, I think, referred to as almost fully connected in the OAM spec, and this effectively allows for all communication with 6 links amongst 8 modules. We also want to be able to support multiple product generations. So I know PCIe Gen 4 has been discussed. We want to be able to support PCIe Gen 5 and beyond. So that's important. Multiple interface types. So PCI Express today as kind of the standard host interface, but we're interested in Infinity Fabric, CXL, other host interface types, and then additional interconnect topology, which we've heard a lot about earlier today for scale-out interconnect and also downstream links for other purposes. So basically, I guess in summary, the call to action here is, the industry benefits from standards, and obviously one of the obvious ones is PCIe form factor cards. These accelerators for HPC and machine learning have a lot more connectivity, and therefore PCIe form factor wasn't sufficient. So I think it's wonderful that we've got OAM now to help facilitate usage of these. One size doesn't fit all. So we've got UBB 1.0 kind of coming into place. There will be other things in addition to that. Eventually, other versions of UBB I'm sure will be developed. But OAA provides building blocks for doing multiple different things. And I guess I'll just say, please join. Maybe I'm sort of preaching to the choir here, because maybe you're already all involved in this OAI JDA. But the bottom line is, ensure that your use cases are covered. Join the conversation. So thank you.
Thank you. I'm going to hand over to Olaf.
Is everyone going to go up here now? Or? Okay.
Yeah. Olaf, I'll have you introduce yourself.
Okay.
I'm setting up this.
So, hi, I'm Ola Tørudbakken. I'm the SVP of Rack Scale Systems at Graphcore. Graphcore is a startup building intelligent processors for machine intelligence. Before Graphcore, I was at Sun. Back in 2009, we had 4 of the top 10 largest supercomputer in the world, and after that I went to Oracle and built up the engineered systems. So what I'm going to talk about here briefly is building large-scale machine intelligence systems. So if you look at machine intelligence 7 years ago, it has made a phenomenal path. So we started out with simple static data, relatively trivial image classification, object detection, used and deployed on today's hardware, CPUs and clusters of GPUs. What we see for next generation workloads is that the systems needs to basically start to develop context and understanding, and basically develop what we commonly refer to as common sense. So just two graphs here. The one on the left side basically shows the compute that has been growing over the past 7 years. It's petaflops per days in terms of training. So it's roughly a 7x CAGR rate. More interestingly is the growth in models, which is shown on the left-hand side, on the right-hand side, sorry. So the CAGR rate of that is basically twice the compute. What I expect is that within next year, you will easily see models that is in the billions or trillions size. Traditional architectures that has, take for instance GPT-2, 1.5 billion model parameter, that cannot fit into traditional GPUs or other systems based upon HBMs. So you need to spread the model across multiple chips. So interestingly, just as a reference, how large will actually model grow? How large will the data set grow? Well, for the training data set, that is pretty much infinite. Whitney here can probably talk about the amount of storage that Graphcore, that Facebook use to store pictures, videos, and so forth. It's effectively unlimited. How big can a model be? Well, the brain is around 100 terabytes. The long-term memory is around 200 megabyte, and if you want to scale a model by n, then the compute scale by quadruple or at least. So where does that leave us? Well, Graphcore, what do we do? So we have built a new processor for intelligence. It's really two main different things that are different with this processor from other processors. Well, it has a high peak flop, and it has a high number of cores. Well, many companies is doing that, but it has around 50 to 100x higher memory bandwidth than others, and all the communication is compiled. So you remove all the jitter and latencies that is associated with communication when you build large-scale systems. So what have we done? So we are building a really scalable system solution to train these trillion model machine intelligence models. We leverage OCP. We use a regular 1U networking chassis. Leverage the Facebook 1U wedge design. And we stack them together. So totally 4K IPUs, fully connected, can be securely multi-tenanted, so you can run multiple applications, multiple users on this. Of course, Kubernetes enabled. So that's what we do. So how does this fit with OIA and OAM? Well, clearly, Graphcore, as the other companies here, we are very much a big fan of open standards. The current chassis that we have is based upon OCP, the network chassis. We are actively monitoring the module evolution. To us, it's not completely clear that there is one size fits all. There might be vendor-specific things in terms of data prep, in terms of disaggregation, and in terms of how you actually do connectivity among solutions. So that may impact both the OAM and it may impact the UBB, and the host interface board. But definitely a right step in a good step in the right direction, and we are, again, monitoring this very closely. So, thanks.
Okay, I'm gonna invite all the panelists and then for the discussion. Since I received these slides before, so I actually prepared some questions to ask.
I'll take the last one.
Okay. So Siamak and I are wearing now our OCP shirt, and then yeah. All right. I'm gonna go one by one then. Let's start from Nvidia. Rob.
Sure.
So, what's the motivation for Nvidia join OAM OAI?
Yeah.
And what's the next steps?
So, okay. It's a good question. So, whether people know it or don't know it, in NVIDIA, we already make something that's very similar to OAM. It's called NSXM. We're working on our 4th generation product now, so which is probably why this question. OAM is really interesting. On the one hand, we drive our own platform and our own module spec, and that allows us to have control of the entire system and create something very fast time to market, very fast to solution, so that we can accommodate everything, and compromise everything in the system. On the other hand, there are very large data centers like Facebook or Microsoft who like to have something that's very methodical, that they can deploy, they can have consistent design that fits their data center, something like OAM, and that's really important to us too, is making sure that our key partners are able to deploy in the way they want. And so OAM really satisfies that. We'll probably continue driving our own path for time to market and pushing ahead. This industry really is changing month by month, as Misha said in the keynote, and in order to keep that cadence, we have to push the envelope all the time. But we also need to be able to accommodate large-scale deployments.
Thank you, Rob.
Yeah.
I think as a OI open group, really welcome and excited to have NVIDIA join us in the journey. Yeah, that's our goal, to have the open standard for everybody.
Yeah.
Okay. Siamak, you have any question for? Okay, I'll go through my list then. Okay. Frank? Yeah, I've been working together for this OEM spec for a very long time. I heard what you just said. So what's AMD's plan moving forward? We have a product concept, right? What's the next step?
Yeah, so I'll just elaborate a little bit more on what I said earlier. Obviously we've observed what Nvidia has done in the past, and it was kind of clear after discussions with many cloud service providers that trying to extend the PCIe infrastructure wasn't going to cut it for that kind of connectivity, and so then in our view, we were going to have to go it on our own also. Yeah. And so we were kind of heading down the path of trying to define our own, if you will. And so we were very happy to have the opportunity to collaborate on something that could be a standard. I will say, kind of similar, I guess, to what Rob said, we're going to be doing our own stuff as well, right? So OAM is, as I said, it's a superset. And so there are some aspects that are going to be common and interoperable, but I think other vendors, I think even Olaf, you mentioned also, hey, maybe not. It's not one size fits all. So like the way I personally view it is, it's a superset. OAM's a superset. UBB in its first incarnation is a subset. And then there's also, I think, a couple of flavors that were mentioned already that are in existence. One of which we're going to interoperate with, one of which we won't interoperate with. But for AMD, I think what you're going to see is we're going to use OAM. The first generation was defined in order to support, let's say, PCIe Gen 4 with extended speed mode, PCIe Gen 5. We want to collaborate on what comes next, which includes PCIe Gen 6, I imagine. CXL seems reasonable. And then what you're going to see is we're going to take advantage of different flavors. And so, as I mentioned, by 16 links, we understand the need for also being able to support, for example, by 8 links and things like that. So I think what you're going to see is more capability from AMD moving forward, and more flexibility from AMD moving forward. And then there'll be a mix of things that are absolutely universal baseboard kind of based versus things that are just absolutely, I hate to use the phrase, but A plus A, that are very tuned systems, right? So I think I may have alluded to this before, but Infinity Fabric as host interface, for example.
Yeah. So I want to follow up question. So kind of we are in the process to setting up the infrastructure, right? We see Intel Graphcore, and we all have a real product. Is that any plan for AMD to launch a product that's using OAM form factor?
Absolutely. I just can't say anything about the timing of that,
Okay.
or anything about that specific thing. Yeah.
Yeah, hopefully
Yeah,
it's in
yeah,
the
absolutely,
very
it
near
will
future.
happen. It's just a matter of when. Yeah.
Okay, we'll be exciting to see that moment. All right, thank you, Frank. And then for AK, I noticed that you spent some time to talking about the interconnect link, the ICL from Intel. Earlier, actually, I mentioned for the scale out, we have a different approach, either like Nvidia side, right? We can use the InfiniBand or Ethernet card to do the scale out. And then Intel looks like are using a different approach. And then your interconnect link actually supports the peer-to-peer direct connection. So what's the benefit? What's the pros and cons? And from performance point of view, can you talk about it?
Right, and that's, I think, a very good question, Whitney. And I think that is a critical part of the solution, I think, to get to tractable time to train for these large-scale models. As I mentioned, and I think Olaf mentioned also, that we'll soon have trillions of parameters. And some say, to get to let's say common sense or general intelligence, you'll probably need like 100 to 500 trillion parameters in your model. And so to get to a time to train number where you can actually work with, you need large scale training systems, maybe 50,000 processors. And so when you think about, okay, how do we connect 50,000 processors in an efficient way where you can still get that performance scaling, and your scaling efficiency is not cratering as you continue to add processors? How do you do it? That's when you have to come up with a fabric that is high performance, low latency, and can be clueless. And so we've looked at definitely Ethernet, InfiniBand. We look at that every day because that is the fabric that's there in the data center today. And from our analysis, the Ethernet InfiniBand fabric is awesome, it's great, but from our analysis, it's not sufficient to get to that performance and performance of our TCO that you need to get to be able to train, let's say, a trillion parameter model next year in a tractable amount of TCO. and the ICL protocol actually is based on our years of experience on HPC computing, and it's based on what we think is a high performance, efficient, glueless fabric. So that's why we are going to pursue with this fabric. Now we may support Ethernet InfiniBand also, because some we do see some customers that have hesitancy on adopting a new fabric in the data center. So there is this bar of being able to roll out a new fabric in the data center. We realize that, but I think from our analysis, again, to get to that trillion parameter model trained in, let's say, a couple of days, you need this kind of a fabric, this interchip link kind of a fabric.
Just a quick question onto that. So does Intel see with this OAM and the interconnect fabric, does Intel see a resurrection of the OMNI path? Or is that
So this interchip link actually, if you, and we haven't released that deeper dive, level of microarchitecture specs, but it has commonality to our OPA fabric. As I was saying, the genesis, the architecture of the interchip link fabric is based on our HPC experience over the years, and OPA is part of that experience. So yeah. So it does lean on what we've seen with our OPA experience.
One follow-up question. So I understand the fabric and the transport and this can be optimized, but what about flexibility in terms of topology? Because in the picture that you had a specific topology, which is some sort of a ring with the dense interconnect between four. Would that be kind of fixed, or are you guys looking at flexibility in terms of topology itself?
Yeah, so it goes back to how do you train a trillion parameter model? Do you do is data parallelism enough, or do you have to go to model parallelism, or do you have to go some other architecture? And when you go to even model parallelism, right? Model parallelism is really you are serializing layers, right, at a high level, and so you need different kinds of topologies to efficiently get through your training. For example, if you do model parallelism again, right, you will be blocking a layer. Will be blocked till the previous layer gets done, right? And so you do need different topologies, different types of maybe crossbar switching to be able to train in a tractable amount of time. And so we are looking at different topologies for sure. For sure, it feels like we need to go to model parallelism. Also, how do we handle sparsity, right? The large scale recommendation systems are becoming more and more sparse because of the ordinality of some of the data, right? And so how do you deal with sparsity? So you will, I think we will see different types of topologies as we go along.
Thank you.
Questions perhaps to Olaf?
Yes. Question
Do you mind if I follow up on that last one? Actually, it's I was just going to say it was a great question. And the fascinating thing we struggle with at NVIDIA on topologies and communications is, one, as you scale out, it really becomes a bandwidth test more than computation or anything else, right? And two is what we're seeing is even within one network, at different stages in the network, as you cycle through the training process, you will have completely different communication patterns. And we struggle with that because there are situations where you want to have all-to-all, and then you might want to do an all-reduce. You might want to do something that looks more like a communication network, and then something that looks like memory communication with an address data. And so it is a real struggle to come up with something that covers all of those simultaneously, and it does need to be simultaneously. And over time, we're probably going to add on new communication topologies as well. So really critical aspect, and I guess the overwhelming approach that we try to take is to cleverly eliminate as much of the communication as we can. And that's, of course, never totally possible. But reduce.
Siamak, you.
Similar questions, but I'm going to try to rephrase it, perhaps to Olaf. As you have seen, within the OAI, we are trying to create an environment that the environment itself is common so that different solutions can emerge. We're not prescribing that all solutions be the same. We're saying out of all of these links, out of so much power capability, out of so much infrastructure, use whatever you can the best way it can. So do you see convergence of solutions, or do you see specialized solutions emerging, still using a common platform?
Good question. So before I answer that, let me take a step back and talk a little bit about communication for machine intelligence. So first of all, if you look at the brain itself, I mean, roughly a quarter of the brain is computation or memory. 3/4 is communication. I basically built InfiniBand systems for 15 years. I participated in the InfiniBand spec standardization in 99. I still held the world record in terms of switch latency for InfiniBand switches. Back in 2004 at Sun, we built a switch with 83 nanoseconds latency. I know InfiniBand. Machine intelligence or communication for machine intelligence is completely different than traditional networks. Well, at the data center level, you still have requirements for HA and so forth, but fundamentally, when machine intelligence, the communication pattern that you expose today is very much peer-to-peer. Bandwidth is really important, as my friend here just said, and collective. All reduce, all gather, reduce scatters. Really, really important. The second part, from a system point of view, I mean, that is the north-south communication. Basically, the host to the intelligent processor or GPU or accelerator. So if you go 10 years back and look at when Nvidia started to ship GPUs into in particular at that time HPC data centers. So, Tsubame in Tokyo was one of the first. You typically had a ratio of 1 GPU for a dual socket server. Then it gradually increased. You had 2 GPUs, you had 4 GPUs, 8 GPUs with DGX1, now you have 16 GPUs. If you look at, again, the workloads, take NLPs, the fact is that, the host or the CPU requirements to support NLP is far less. So you can actually easily, live with a ratio of, 1 to 100 or even 1 to 1,000 in some cases. Image detections or video, on the other hand, would require a completely different ratio. So you need to have, traditional PCI, which has been more like the key interface to these accelerator to the CPUs, may no longer be the right choice. A traditional data center network like Ethernet might be a better choice. And that also from a system provider or data center providers may allow even more flexibility because you can stick with your regular service, SKUs, connect them to your data center networks, and then you have your accelerators SKUs on the opposite side. So, and that kind of also brings me to some of the challenges. I mean, going back to the question you asked, Siamak, about the convergence. Again, I think me, as anyone here, we would like to see convergence happens at this level, because standardization, that is really good. Standardization is great, but there are different requirements in terms of power capacity. There is different requirements in terms of bringing out the chip-to-chip interconnects, and there are different requirements in terms of providing the host connectivity. But I'm really happy to see that OCP has started this journey towards something. Whether we end up with HIB or OAM as currently specified, 2-3 years down the road, I don't have a clue. Maybe somebody else here.
None of us know what the future is, but we could imagine something better. So commonality is great, but as you guys have said earlier, individually, different companies have tried to go as fast as possible going alone. We've said that before. And then the question sometimes is, can we go longer if we go together? Or could we even do both? Within the infrastructure that we're creating, we're not limiting innovation. We would like you to guys actually do it alone if you like to, for a little while. But once you require a specific thing, we want that requirement to come back to the community so that the community can work together to help you go faster, go farther. That's one point. Second point, the UBB platform that we're creating, we have a bunch of wires. Wires are wires, and you can have the protocol of choice running on those wires for peer-to-peer. And that works very well as long as we have a homogeneous intercommunication path, homogeneous acceleration need. But as you think farther in the future, do you see different layers of these neural networks might benefit from different computation elements that might come from a different company? Do you see that we might want to have a heterogeneous collection of these OAM modules? And if we do, what should that interconnect be? That interconnect cannot be proprietary anymore. That interconnect needs to be somewhat standard. Do you have recommendations for that standard?
So let me take the question first, and then and I'll pass it on. So to me, I think we need commonality at the software layer for sure, right? Now, whether the hardware, protocol needs to be the same or not, I think, I'm not sure whether that's required. As long as the software API, right, that folks from Microsoft, or Facebook, or the folks who are actually doing the data science, right? So I want to separate the data science from the engineering aspect of it. And to me, to make sure the data science is going as fast as possible, right, and is leveraging as many people and leveraging the ecosystem as much as possible is what we want. And for that, I think software is what needs to be common. Now, hardware-wise, yeah, it'll be good if we have the same, wiring, same protocol on the hardware, but I think software is more important. And we should definitely strive to make sure that we support, the software being the same.
Yeah, I'm not actually sure I agree with the software being the same. I think it's still too early to predict what that's going to happen. I mean, today we have people using different frameworks for very, very legitimate reasons. They're better at different things. So it's going to take. I think it's going to take a long time to evolve to any sort of standards. Mixing things is going to be really tough. So I just said, I don't think we. Well, yeah, but that means the more things you keep homogeneous, the easier it is, though, right? So having just said that, I think it's too early for standardizing software. I think you need standardized software to start mixing heterogeneous devices and getting them to communicate together. And so I think that we're really early in the evolution. I think it's going to be a while before we get there, and how that shapes up, I think we can't predict yet. I mean, things keep appearing. I mean, BERT, for example, this amazing network. 6 months ago, nobody knew it, and now just about everybody has it in production because it's so awesome. It happens to be gargantuan. It works really well, you know. So things on a 6-month cadence, stuff comes out and shocks us, and it changes the world. So I have a really hard time predicting.
Just a side comment on that too. I mean, 3 years ago, anyone heard about TensorFlow?
No, exactly.
So take a step back. That's why we started this journey. Like Misha yesterday mentioned, it's 1% finished, and then also this is why we wanna us all get together to collaborate and see how we can converge. I do see open standards like benefit everybody. Like I like to go back to our infrastructure, right? One thing, I guess, since we have the UBB, and during the design and spec discussion, one thing came out is when we do the scale out, AK just mentioned about the proprietary protocol, and then moving forward, and then we do see pros and cons there. And the other thing is by using different way to do the scale out and moving forward, right? What's your view for the future, like OAM or OI group, that we can do to help the convergency? Yeah, here. Specifically, I like to ask your view about the scale out. I will not say protocol. I will say protocol. Yeah, takes time to converge, right? And then moving forward, how do you see when we do the scale out, how this group can help? And then what's your view for the maybe next step?
I'll go on this one also first because, as you know, I've already pinged you, Whitney, about our OAM 2.0 spec, right? And when can we start? Because we do see that, you know, the OAM 1.0 already, you know, running out of juice for what we...
Yeah, first I like to hear feedback, whether we have some feedback for 1.0, right? And what we can do for next year. Right. Maybe 1.0 is still okay, but... we need to work with accelerator supplier, like OEM supplier with you, and then we can moving forward to see 1.0 can fulfill your roadmap or the trend or not.
Right, and I think it goes back to what I had started off in my talk, which is both AI compute and AI communication, right? Because the workloads, are changing, right, and are changing, I would say, exponentially, right? And we're seeing that. I think the specs need to be flexible, and I think agile to be able to go where the market needs to go where the customers need to go. For example, let's say we figure out that hey, we need to go to 800 watts, right? Because that's what we need to do to get to tractable time to train on a 1 trillion parameter model. And so if the spec says, hey, you can't go there, then for sure we'll do our own custom modules, right? Because that's where the market wants us to go to. Similar on the communication, right? So the communication, I do think what we have in OAM 1.0 is good. It's good for next year, but I'm not sure whether it's good for the trillion parameter model or not. I think we'll find out. Maybe maybe my friend here will find out first, but but I think we'll find out whether the OAM 1.0 is sufficient for a trillion parameter model or not. So I would recommend let's be flexible And I think, as I was saying, as I pinged you, Whitney, initially, that so today we've closed 1.0 OAM spec and we're working on UBB, and it feels like the work group is not going to go back to 2.0 spec till we finish the UBB 1.0 spec, and maybe that process may not work.
Well,
He wants to work on the 3.0.
they,
We
we are at the beginning of this journey. We have articulated a modular system. And as you guys very well know, you can fork all of that. You can run them all in parallel. It's just quite all right for a new team, start working on the OAM as the 2.0 while we are still finishing up UBB and host interface board and expansion modules. And as we need to step in, figure out what we're doing right and what we're not doing right, receive feedback. It is a totally open source. We did not wait for completing the spec before we publish. We are talking about the concepts even before writing them down as specs. So that we can get feedback, so that we can get direction for where to go next.
Yeah, I guess my only comment is there's a practical aspect to all of this as well, and that is, I think generally people have products and they've got a roadmap for products, and so like from an AMD perspective, it was like the OAM 1.0 was specifically to cover like a PCIe Gen 4 kind of product with ESM capability and a PCIe Gen 5 product. That doesn't mean the nth generation of Gen 5. It just means the first one. And so, yeah, we would love to collaborate on the next one as well. We see optical coming eventually. We see PCIe Gen 6. We see all kinds of things. And so, yeah, let's just collaborate on those as well. I mean, we started this thing together. Let's continue. And like I said before, what we should do is what you said, Siamak. Let's leave the flexibility in there so that, if somebody has a better mousetrap, they can implement the better mousetrap. And then everything will be self-correcting. If there's a better mousetrap, we enable the better mousetrap. Eventually, people will migrate to the better mousetrap.
so
Just to add to what you asked about, I mean, what can you do? So 2 requests. So one challenging thing today, I think that was also brought up in an earlier talk. If you look at that is signal integrity. Currently, you basically have 3 boards. You have an HIB, you have a UBB, and you have a module. And the chassis to chassis interconnect that goes usually through the HIB, through the QSFP-DD or OSFP. As we increase the speeds of the SerDes, the having to cross more like 3 connector hops just to get to the end of the chassis, that is a very, very challenging thing. The second thing, that is, of course, if you look at silicon today, I mean, 7 nanometer. If you look at NRE there, I mean, even though some of the companies have bigger wallets than others, it's still a fair chunk of NRE. So what you typically do, I mean, Nvidia have been doing it. I believe also the other guys down here has been doing it. They optimize, they build, they use the largest die as possible. And a large die, that usually also implies high power. So from that point of view, so you need to support high power, and you need to support lots of breakout signals, because the connectivity, that is really key. So the model size, and that may also be something to look at.
But I'm going to try to turn this one into a request to all of you guys. Yeah. So based on the current definition of OAM, I think for a while we have enough wires, enough power, enough space. What we don't have handled so far is the signal integrity problems you mentioned.
Yeah,
So for that, since we are building modular structures, at the edge of each module, we have a concept of demarcation point in the form of retimers today, so that we can break the signal into multiple smaller pieces to achieve the bit rate that you were thinking. But the problem we have, once we do that, then the concept of wires are wires don't apply anymore. So if I want to support OpenCAPI, or if I want to support Infinity Fabric, or NVLink, or CXL, and if they're not using the same physical layer, we will have trouble. We will not be able to speak English and understand each other. If we're speaking different languages, that's kind of hard. So perhaps the request to you guys is, you did go alone for a while. You found the best thing you wanted in your interconnect, in your topology, in your protocol that you're using. Well, if you want to go together, when you're thinking about the next thing that you want to do, we should, at least on a physical layer, come up with a solution that can accommodate all of this. And maybe we will be better together.
So I'll see your request and I'll raise you.
Raise it.
Yes. So I track a lot of things in this industry for myself personally, and after a while I started seeing some patterns. And over the past 4 years, it seems pretty clear to me that this industry, the AI industry, and the demand has been requiring about 10x the capability. Whether that's compute, communication, memory bandwidth. It's around 10x more every year. That's really hard to squeeze out of normal old improvements in IT infrastructure. And so the thing I would ask for in the next OAM is to aim absurdly far ahead, because by the time we're done with it, it'll seem very, very prescient and it'll be right on. So I would argue that, a year from now, a lot of the specs of the OAM are going to be weak, and we'll suffer for that. But if we aim way far ahead, then we probably will land in the right place.
Just tell us which direction.
Actually, that is the problem. It's every direction. I mean, and this is one of the unique things, that we hit the roof lines in intra-node communication, inter-node communication, memory bandwidth, compute capability, device to device, like host to accelerator bandwidth. We hit the roof lines in every single thing, and then we have to push through those. So we need to hit all of it.
But please, all of you guys,
Make sure we
say
talk.
the same one.
Exactly.
And you guys too.
Yeah.
You mind if we ask a couple questions?
You
Sure,
should
yes.
join the panel. You should join the panel.
No, I probably shouldn't. But there was one comment that was made about convergence on. Okay. There was one comment made about convergence on interconnects, and I think somebody's.
Introduce yourself, please.
Oh, sorry, Paul Lecoq, IBM, working on OpenCAPI specifically, but that's not what I'm asking really. But you mentioned that convergence was going to be very difficult because from a heterogeneous accelerator point of view, and I agree with you. I kind of agree with Frank's statement that A to A will always have an advantage over an A to B. Yeah. But from a host to accelerator point of view, I think we can have a convergence. I think we need to for the companies such as Graphcore or Nvidia that don't have a processor. They don't have a host. So they're at a distinct disadvantage if there's not a commonality. And I think we negate the innovation of a lot of companies if we don't get that convergence. So do you see a better chance of host to accelerator convergence beyond PCIe?
I think CXL is the natural thing that's going to happen. I think CXL is the natural progression off of PCIe for that specific purpose. Yeah.
I would say, although CXL itself is Rev 1, it needs a lot of help still before
exactly.
it's truly useful in this domain, I think.
Join the CXL consortium you have, and,
Yes.
and let's work together on the technical aspects and solve it. One last comment on everyone. They're kicking us out.
Okay.
We are half an hour over, and it's a wonderful discussion so far.
Thank you.
Whitney, please.
Yeah. I think we just need to find some time to continue the discussion, and then always like get connected. Make sure that we go the same direction, since we're solving same problem here, right? I really like to collaborate more to see especially like when you plan your next generation AI processor, right? We do need align more and better. Since the first generation OAM was designed and a lot of accelerator already on the way, so I think we've been making great progress. But moving forward, right, we do want to see like more convergence and then more collaboration between.
Right. Last year when we were talking all amongst ourselves, nobody thought that we were serious when we were talking about a module that could be compatible and a lot of good people could design to it. But the sheer amount of number of people who have come along and raised hands who want to help is great. It's awesome, very encouraging. We would like to publish a good 1.0 version of the spec by March. OCP Summit is our target. So we need a lot of help, guys. We need help from you guys, let's just work together and see if we can publish that.
Thank you. Yeah.
Okay. Thank you very much.
No pleasure.